An Energy Department project called the Quantum and Space Collaboration has drawn in several industry participants. Energy says, in its own words, the collaborative aims to harness cutting-edge quantum technologies for pivotal advancements. Here to translate, the Senior Commercialization Executive in the Office of Technology Transitions, Rima Oueid. Good to have you with us.
Good morning. Thank you for having me.
And from Accenture Federal Services, the Quantum Security Lead, Garland Garris. Mr. Garris, good to have you with us.
Hey, Tom. Great to be here.
All right. Ms. Oueid, tell us what is actually going on here. This is not quantum computing per se, but quantum technologies in a larger sense?
It includes quantum computing. So there's a cohort of us in Federal Service that realize a lot of us are trying to do the same thing, but we were doing it separately. And we know that quantum technologies behave differently in space. And also there are use cases that benefit various agencies if we had quantum technologies in space. So that includes quantum computing, quantum sensing, which provides imaging, position navigation and timing, and then also quantum secure communications. And so we do a lot of communications through space already, but it is not quantum secure. And so this is an opportunity for us to be able to leverage each other's resources and create a Manhattan-like urgency around innovation in quantum. Competing in space is really important, particularly in this sector.
Quantum computing doesn't really exist in any production sense, though, does it?
So what's interesting is we know that we need to be ahead on quantum and computing in particular. We know that quantum mechanics behaves differently in low-gravity settings. And so what we may not be able to accomplish here on Earth, we may be able to accomplish in space.
It's cold enough up there.
It's cold enough, but also the actual mechanics of the crystals that we want to produce, not just even for quantum computing, but even for semiconductors, are better produced in low-gravity settings with fewer defects. So we could manufacture in space and get different outcomes. We can also apply things in space and get different outcomes. And our algorithms might behave differently in space as well if they're running on a quantum computer. But there are some near-term applications or near-term quantum computers that we can use today. What we're lacking are the algorithms. And actually, Google just launched a prize competition around this to find those use cases, which I think is probably been partially inspired by some of the work that we've been doing because we've identified over 200 use cases just in the energy sector. But again, the algorithms are missing, and that's what we need to work on.
All right. And Mr. Garris, Accenture Federal Services, you're a major participant in this quantum project. What do you bring to it?
So we're working in a number of different areas, primarily focused on helping agencies comply with policy and legislative mandates right now, and that's focused on quantum security and protecting agencies from the threat that quantum computers will someday be able to crack cryptography they use. And there's a few policies that are directly relevant to that, M2302, NSM 10, and then what was House Bill 7535 became the Quantum Computing Cybersecurity Preparedness Act, and it laid out some specific requirements for agencies for, first, determining how they use cryptography now, and then coming up with a transition strategy for this generational change of technology, which doesn't happen that often. So this is going to be a multi-year effort. So we're helping agencies there. We're also working in areas of quantum information science within certain parts of the DoD. They're focused on looking at R&D, combining quantum computing and exploring the intersection of ML and artificial intelligence. And all these are very emergent areas, which we're helping the government explore. And then also in the context of communications, the U.S. government, and I hate to put it this way, but we're a little bit behind in the context of global spend in quantum research. And if you would look at how we compare, say, to China, the U.S. government and the public sector is spending a little less than $2 billion a year. China's spending about $15 billion. And they have a significant R&D effort with quantum key distribution with their satellite network. And that's something we're looking into as well.
Right. Now, the things that come to mind are, one, on the encryption side, the NIST at the Commerce Department has come up with proposals or drafts, I guess, of quantum-resistant encryption algorithms, and we're talking about space. So are NIST and NASA part of this whole thing? Rima?
So NASA is involved, yes. But what NIST is working on is the post-quantum cryptography. But we're looking beyond just the post-quantum cryptography. We're looking at things like entanglement for secure communications. So it's different protocols and using sensors as well, so quantum sensors.
What is a quantum sensor?
Well, there's lots of different types of quantum sensors, but they are able to detect anomalies and also capture images at much more precise levels and be able to see through the ground from space, see under the surface to be able to identify from a Department of Energy standpoint, things like geothermal, water where we didn't know water may exist, caverns where we can store carbon, do oil and gas exploration in more precise ways so that we disrupt the environment less. And then also to be able to see in the ocean, which is also important for offshore wind sighting. And then obviously you can imagine what the DoD use cases would be in that area. So quantum sensing is actually kind of the unsung hero in a lot of this, I think. It's a technology that has been around for 20, 30 years. We've been using quantum sensors in MRI machines. We use them in atomic clocks. GPS uses it. But because of the distance, GPS is easily spoofed, jammed, and hacked. And energy infrastructure depends on GPS. Cars, automated vehicles, all these things that we plan for utilizing in the future become potential targets for malicious actors if they're not secure. Imagine a malicious actor hijacking GPS, one brand of vehicle. I'm not going to name any because I don't want to upset anyone, but just imagine the implication of those vehicles being hacked. And they don't have to be EVs. We use them today in internal combustion engines. So
a quantum sensor then is something that is composed of elements that are not binary, that is one state or the other, but they have many intermediate states. That's my basic rudimentary understanding of quantum.
So that's combining a couple of different things, but quantum sensors will enable you to have precise measurements that greatly exceed what we can do now with GPS alone. So down to a millimeter, for example. And if you're the Department of Defense and you have a UAV, you can have 100% confidence that it is not going to be jammed. It's going to work, 100% of the time. Instead of using triangulation with cell phone services, you're going to have pinpoint accuracy where a device is. And as Rima indicated, it can be used to detect things that you can't use with other measurement tools. As far as, the other topic, I think that's really getting into quantum computing and how quantum computers work, which are quite different than classical systems. Yeah.
And this is not a physics class anyway, and I don't understand the physics, and nobody probably listening would. But let's get to the practical side of this. You're going to have to put things in space to do things. Describe for us what an experiment might look like, and what would the outcome you would hope for would be, and what would go up there, and by what means would it get there?
So we're starting off with some of the easier technologies, things that are already commercially available. So we know that quantum entanglement for secure communications already available, and we are looking to demonstrate the ability to be able to use that in communications from satellite to ground. And we can start by putting something up on the ISS.
The space station.
The space station. There's already a Bose-Einstein condensate, so it's a quantum sensor, so not part of communications, but that's already been put in space, and that's where we realized that these devices behave differently in a space setting, and we actually can create different types of connections and different abilities for sensing things in space.
And is entanglement, you used that word a couple of times, is that the same as scrambling a signal or encrypting it in some way?
It's more about the secure communication.
Right.
It's a connection. So if it's intercepted, if somebody tries to eavesdrop, that connection gets dropped. It's unhackable.
The observation of it is what stops it.
Correct.
There's a principle of that, and I don't know the name of it anymore. So it sounds like DoD would be part of this also.
Absolutely.
Yeah, there's a lot of, joint efforts between Federal Civilian Executive side and then DoD labs, DARPA, AFRL, which overlap to a certain extent. And entanglement itself, that is a rabbit hole. You can go down. There's a lot we don't understand. And in fact, the Nobel Prize was awarded to 3 gentlemen last year.
I think you meant it'll go down a wormhole, not a rabbit hole.
Potentially, I guess that's a better analogy. But they were awarded the prize for proving that it couldn't be explained. Rather that hidden variables, which was the traditional thinking, explained how entanglement worked. They proved that that's not the case. So, and a hidden variable is easy enough to understand. I'll give you just a really quick analogy. If you have 2 golf balls, one's black, one's white, and your best friend is Elon Musk. And you convince him to take one of these to Mars. They're in a box. You don't know which is which. And then after that rocket arrives on Mars, then Rima opens up her box and says, oh, I've got the white one. So therefore, you know the black one's on Mars.